Ladies and gentlemen, dear colleagues, thank you for joining this session. My name is Matjaž Mikoš, and I would like to present the results of an extreme May 2018 debris flood case study in northern Slovenia. I would like to acknowledge the contribution of my co-authors coming from University of Ljubljana and the Geological Survey of Slovenia. I would like to give a short overview about this presentation that was published as a technical note in our journal Landslides last year. I will give a short introduction to the event. I will show the analysis and modeling of the event. I will wrap up with the mitigation measures planned and draw some conclusions or lessons learned from this case study. So a few words about the study area, which is located in the northern part of Slovenia. You have here a digital elevation model of Slovenia and the ski resort Krvavec area located. So we investigated two small but steep torrential watersheds, which are located below the ski area where the Krvavec rainfall station is located. In these two watersheds, several events, being hyper-concentrated floods with intense sediment transport or debris floods, occurred in the last 30 years. The last event, presented here today, happened in May 2018 during a short but strong thunderstorm. So the main characteristics of the two watersheds: both torrents are small, around 2 square kilometers. Catchment area is pretty steep, more than 50%. Slope of the torrent, 25 to 30%. And the land use mainly forest, and the rest is agricultural area. Now, some thoughts about the consequences of this extreme May 2018 event. There is a collage of photos with the arrows so that you can see where the photos were taken in the both torrents. So we can say that the extreme rainfall event caused intense erosion processes that led to debris flood. The main source of the material was the Brezovski graben, where in the upper part there is still a lot of potential material located, let it be in or close to the channel for future extreme events. In the lower part of the torrent, the slope is relatively high and not much of deposition can occur in this area. So most of the material from the Brezovski graben was deposited in 2018 near the cable station. We have a photo of it, where the maximum deposition height was up to 3 to 4 meters. The volume of the deposited debris material was estimated at 7 to 10,000 cubic meters. Let's go now to rainfall analysis of the event. We had at that time 2 rainfall radars and we used their data. So we have in B, C, and D rainfall rate as measured by rainfall radars in the first, the second, and the third hour of the event. Furthermore, we had pluviohydrograph and optical dysdrometer data. We know for dysdrometer data that in literature, several studies have already indicated that optical dysdrometers tend to overestimate the drop velocities, hence can affect the calculated rainfall amount, which was also much higher in our case. So if we take the statistical analysis, the 30-minute rainfall was measured by pluviographs to be of a return period 50 to 100 years. Using optical dysdrometer data, this goes to above 250 years. In the field, we have performed a geological survey. So a geological map with some of the details about past landslides and hydrotechnical torrential structures is given here to the left-hand side. And we have seen that the deposited sediments were mainly coarse-grained carbonate gravel, and there were no basically clay or silt fractions available in the deposits. For the hydrological analysis, we used the HEC HMS model. We used the CN curve 68, and we have computed the SCS unit hydrographs. In table 2 below, results are given for both torrents using rainfall data from pluviographs and from optical disdrometers. We a bit modified that for debris flood simulations in the next step. So a hydrograph with the following parameters was used: the peak discharge of 32 cubic meters per second and the total volume of 48,000 cubic meters. So for debris flood modeling, the Rams debris flow model was applied, produced, developed in Switzerland. The model was then calibrated using the extent and of course also the position of the deposition area as clearly shown in this figure with the Rams modeling results. There are also the contour lines given here, and the spacing between them is 100 meters. In colors, you have the deposition height. Red goes to from 6 to 7 meters. We have notified that the calibrated set of model parameters was different for Brezovsky Graben and for Lukensky Graben. The stop parameter was basically the same. The other two model parameters, mu and xi, were a bit different. If we wanted to get the same set of calibrated parameters for both torrents, then the release area should have been made flexible, not taken here as proposed from the May 2018 event. Now, a few words about the mitigation measures, and for that, we have done some calculations. Firstly, we were using some empirical equations given from different authors to estimate debris flow volumes that can happen in these two torrents, and in both cases we get something around 20,000 cubic meters. Then furthermore, we use the base grain software developed in Switzerland to estimate grain size distribution of debris material, and the result what as the maximum size is 40 centimeters. Then we decided to plan a check dam in the form of a slit dam with an opening that should be constructed at the confluence of the both torrents, Brezovsky Graben and the Lukensky Graben. Furthermore, in the upstream area, in both catchments or in both torrents, a series of flexible net barriers were planned to catch the inflowing debris. As a main construction measure, we proposed, as we said already, a new slit dam in the downstream area after the confluence of the Brezovsky Graben here in the upper part of this figure, and from Lukensky Graben coming from below on this map. In both torrents, several check dams with the riprap between the check dams was proposed, and a large sediment trap with a volume of 40,000 cubic meters was planned. The opening of the slit was determined using some equations given here to the right-hand side. We used the Piton and Recking equation, and the relative opening was then determined to be 2 Dmax, or simply 80 centimeters. And for the calculation of the debris flow impact on the dam, we use the Austrian standard for protection works for torrent control, part on actions on structures, where we use the bulk density, flow height, and debris flow velocity of course, results of these numerical RAMS debris flow simulations. So if we can draw some conclusions from this case study, kind of lessons learned from the event, we can say that the simulations using the numerical RAMS debris flow model that were calibrated using the information available about the deposition area in May 2018 yielded meaningful results that validate the empirical approach used for the SLI dam stability design. Furthermore, even though the RAMS DF model is basically meant for debris flow modeling, it was successfully applied for debris flood modeling as it was noticed in the May 2018 event in Slovenia. A SLI dam that was designed to withstand debris flow impact and to trap sediments transported during future extreme events similar to the one of May 2018 was simply proposed as the main mitigation structure in the downstream area. The planned mitigation measures will start being executed as we speak, so in these days, and after that, we think that the Krvavec ski lift station will be adequately protected. If you want to have more info on this case study and the rationale and procedures we have applied, please go to our journal Landslides and see the paper, a technical note that was published in this journal. I would like to thank you for your attention.